Now that we have some of the basic ideas of a hypothesis test, let's discuss how to actually find the samples to the test value, as well as actually perform a test. So first, the test value is actually nothing new to us. It's defined by this x bar minus mu over sigma divided by the square root of n. So x bar is our sample mean, mu is the hypothesized population mean, sigma our population standard deviation, and n is the sample size. And in general, with the hypothesis test, we're going to have 5 steps. Step 1, we want to state our hypotheses. We then want to find our critical value, which we talked about last video. We then want to compute the test value, this thing we just defined. We want to decide if we're in the rejection or the non-rejection region, and then we want to summarize the results. So let's look at a few examples. So we know that the average IQ score is 100, and it's normally distributed with a population standard deviation of 15. Now, we're at a particular school, and at this school, they claim that their students have a higher IQ than average. So they want to test this and see if they're right. And in order to do that, they take a random sample of 30 students and compute their average IQ and get 106.4. And we want to test this claim at alpha equal to 0.05. So we want to know if these students do actually have a higher than normal IQ. Our first step is to define our hypotheses. Our null hypothesis is always going to say that you're equal to exactly where you think you should be. Our alternative, we think these students have higher IQ, so their IQ should be greater than 100. The next step is to find the critical value. Since we have a greater than, we know this is a right-tailed test. So we know this area to the right is 0.05, which means the area to the left is 0.95. Looking at our normal table, we just need to find the value of 0.95, or as close as we can, in the center. And we'll notice we're actually halfway between 1.64 and 1.65, so we're going to use 1.645. The next step is to compute the test value. That said, x bar, which is 106.4, minus mu, which is 100, divided by sigma, which is 15, over the square root of n, which is 30. And if we work this out, we get approximately 2.34. We're now going to look back at this picture that I drew and notice 2.34 is actually in the shaded region, which means it's in the rejection region. So that means we reject H0. We say H0 is false. Their IQ is not 100, so we have to resort to saying the alternative hypothesis is true. This particular school district does have a higher than average IQ. Let's do another example. Let's suppose that for a specific year, we know that the average score on the math SAT was 500. And we know the population standard deviation on that is 100. This time we have a school district that's worried they scored below average, so they want to test that. Did they actually score below average? So they look at a sample of 40 students and find that their average was 495. And we want to test this at alpha equal to 0.10 and see if this school district actually was below average. Our null hypothesis is then going to say that they are actually equal to average, and our alternative is going to say that they were below average. Since we're looking at below average, we know this is a left-tailed test, and alpha equal to 0.10 tells me that shaded area is 0.1. So let's go over to our table. Looking for 0.10 in the center, as close as we can get is this 0.0099, which is negative 2.33. We now want to find our test value, which said x bar, or 495, minus the mean, which is 500, over sigma, which is 100, divided by a square root of n, which is 40. And that gives us roughly negative 0.32. And if I look back at my picture, negative 0.32 is right about here in the non-shaded region. So that tells me we don't reject. So what does that mean? We can't necessarily say that they're not below average, but what we can say is that there's not enough evidence to say they are below average. So we say not enough evidence to say they are lower.